People absent, so if somebody, whenever we start taking notes, take really good notes for your buddies, because they'll be so appreciative and indebted to you for life. They'll owe you their firstborn. Okay. So, moles. They are going to be the happiest unit. You will see them all the time. They are the stepping stone to everything else. So if you don't have moles, you're probably going to have to get to moles in your first step of a conversion process. Conversions don't happen in one step. Most of the time, you're going to have 2 steps, maybe even 3 steps in a conversion. So you're not always going to be able to go, oh, hey, I want to go from grams to particles. No, you're not going to be able to usually go straight from grams to particles. You have to be able to go to moles first and then bounce back to another unit. So if I want to go from moles to particles, what number comes to mind? Avogadro's number, okay, which is 6.022 times 10 to the 23rd. Particles, and I'm writing particles here. In the future for you, please write whichever particle you are speaking of, because if you don't, you're going to think you're in atoms, but you're in formula units, or you're going to think you're in molecules, but you're in atoms. So if you write it out, you won't overlook that part, okay? So particles, in many of these cases, there's 3 different ones per 1 mole. It's always per 1 mole, okay? Now, atoms goes with what kind of chemical matter? If I'm saying atoms, you're thinking elements or periodic table, right? So these are things that are simply elements from the PTOE. Formula units refers to ionic compounds. How do you know if it's ionic? Metal and X, metal and nonmetal, or metal and polyatomic ion. Molecules? Covalent, okay? So make sure you're using your words appropriately. I want you to make sure you know what you're talking about when you say those 3 phrases. Okay, if I want to go from moles to grams, what happens? What do I need? Molar mass. Okay, I say molar mass. It does not mean it has to be moles over grams. Molar mass, it can be grams over moles. It's interchangeable. You can switch them around. But the units for molar mass are always grams per mole or moles per gram based on if your conversion requires that. But generally, I stick with grams per mole because that's what the molar mass is referring to. That was like half a point if you got it wrong on that first one. So some of you guys wrote no units, and you know me, I'm all about those units. Make sure you're with me there, okay? So I would normally just go to the PTOE to find the molar mass, or I would go add it up from the PTOE to get the summative mass. So this is literally just PTOE mass over 1 mole to get from moles to grams. Liters, what number comes to mind? 22.4 liters per 1 mole. So what do you notice about all of these conversions I have written as is? All over 1 mole, because I need to cancel moles. Cancel moles. You have to cancel your units out, and it's really good for you to kind of practice getting into the canceling mode so that you always make sure the only unit left is whatever you want. Because, let's see, Wednesday and Thursday, we're going to start pulling these things together, and I want to make sure you're kind of covering all your bases so you take care of yourself here, okay? So, differences between these things here. This one, what kind of thing is this? A molecule of carbon dioxide, okay? So 1 molecule of CO2 contains how many atoms of oxygen? 1 mole contains 1 mole of carbon dioxide contains 6.822 times 10 to the 23rd molecules of carbon dioxide. We need to relate just simply, this is 1 molecule. How many atoms of oxygen are in it? 2. This is like the internal ratio thing I was trying to show you with moles to moles. I'm going to try another version, okay? Usually when I grade, I write down the biggest things I see commonly missed, and I cry about it. I'm like, okay, what did I do wrong? I just need to go back over some of the stuff, okay? So, bear with me. 1 molecule of carbon dioxide, I know it's a molecule because it's covalently bound. You need to see the double bonds and everything. Contains 2 atoms of oxygen. Or, if I was talking about carbon, I could say 1 molecule CO2 contains 1 atom of carbon. But this is simply because I'm trying to either get 2 atoms or get to molecules, vice versa. I could switch this around if I wanted to. Or I could say if I was stuck in, for example, I was stuck in moles. 1 mole of CO2. If I took 1 mole of CO2 and I broke it into the 3 parts it was made of, I would have a carbon and 2 oxygens. So technically, this is pretty much saying I have double the amount of moles of oxygen in 1 humongous mole of carbon dioxide. So this is the same ratio, 1 to 2, 1 to 2, it's just different units. So 2 moles of oxygen in 1 mole of carbon dioxide. So either way, this will work or this will work. It depends on what units you're starting with there. You just have to find one way you're comfortable with. I'm going to go back and do both of them over and over and over again so you get the hang of it. Okay, this guy, what is this? Aluminum sulfate, ionic, covalent, elemental? Ionic, so we call this a formula unit. So, in 1 formula unit of aluminum sulfate, how many atoms of oxygen are present?
12.
12. This is 3 times 4, so there's 12 atoms of oxygen present. So you can do an internal ratio from a simple molecule or formula unit or from moles to moles. So we'll practice, I think it was number 4. I need to go back and do. Okay, let's do that one together, okay? Natro started you off with 6.83. Is that right? Is that what number 4 says? Calcium phosphide. Yeah. Calcium phosphide, Ca3P2. Calcium is a 2+ charge. Phosphorus has a 3- charge. How did you know Ide meant phosphorus? Ide goes with periodic table. Or ite, you go polyatomic, right? I actually intentionally put this on there. Number 1, I put phosphate, and on the 4, I put phosphide. So if you put one on the other, you just switch. You go to the other one on the I version. So I just did try to actually help you with your nomenclature a little bit. So if you got calcium phosphide wrong, I took off like either a half a point or a whole point based on the severity of the wrongness, okay? But I didn't take off any points for the process, because if your process is right, thank you so much, okay? So you have to get to atoms of calcium here. So let's go ahead and do this one together. I have one choice with grams. What do I have to go to? I have to go to what? Molar mass. I have to use molar mass. Okay. So 182.18. You got that right? Is that right? Okay. I'm just trying to remember this. Calcium phosphide. Okay, so I'm in grams of calcium phosphide, and they cancel out. Notice I'm actually identifying every single unit with what it's referring to. Calcium phosphide, calcium phosphide, calcium phosphide. All right, so now I'm in moles of calcium phosphide. I could care less about calcium phosphide, right? I could care less. I want to get simply to calcium. So I'm going to go 2 ways here. I'm going to do the new way I just showed you. How many, or what unit do I want to get rid of? Moles. So 1 mole of calcium phosphide has how many formula units of calcium phosphide in it? How many?
1.
Formula units is just simply a particle, yes? How many particles are in 1 mole? 6.022 times 10 to the 23rd particles, aka formula units, just because it's ionic. That's the only reason I'm calling it a formula unit. Okay, so moles of calcium phosphide cancel. If I had to draw out calcium phosphide, I would have Ca2 plus 3 times and phosphorus 3 minus 2 times. This is what a formula unit of calcium phosphide looks like, but in a little bit better, prettier structure, like a lattice structure, right? So that's what that formula unit looks like. How many in 1 formula unit of calcium phosphide, how many atoms of calcium are there, or ions of calcium? 3. It's just an internal ratio. So then formula units of calcium phosphide cancel, and it gets you to simply atoms of calcium. It was like 6.77 times 10 to the 22nd atoms of calcium. I gave some credit on people who had a different way of doing it, like getting percent calcium, multiplying it by grams, doing the moles, going to atoms. I like that method. It didn't come out exactly the same, like 6.6 I think is what some of you guys got. But your method was nice and pretty interesting. I thought it would work out, so I gave you full credit. So, questions on this one? Right, take 5 minutes with a colleague, look through some of your stuff that you can fix by yourselves, okay? This one, I don't do test corrections for test credit, I do test corrections for quiz grades, due Friday. Because if you don't get this now, straight chemistry with reactions is not going to be your favorite thing. So, please look on with a colleague on how to do certain things on plan. If you want to do test corrections on the paper, that's fine, just use a different colored pen. If you want to do it on the paper, fine. Yeah. So now I know. That was what I think I look again for me because I think it's they weren't even that bad analysis questions. They were okay, and I'll look for myself, but I'm not sure. I don't know. I don't care. Maybe next one. I'm giving you 5 minutes now, and if you have nothing to do, start calling at 11. So she was like, if I had to take hindsight 2020, take it to express yourself, but I'm not, I just like to I think so. When I was back All right, one more minute looking at that for now. Asking questions. Calculation error. You just have to be silly. It was like 1.8 times 10 minutes. Calculator. Guys, get yourselves a scientific calculator with some parentheses that promise them to select one answer. I'd like to one gram thing. One mole is always right. 1 gram. No, it's 2 grams. I should run the thing with you. One more molecule is you have to write down molecules. Okay, that's all. The molecule is now moles. Look that. So yeah, you should put your Right, I think that would be harmful to the even in small quantities. Yes, because really what I did. Hey Maggie, did you find us? I had like probably 500 papers this weekend, and I was going to be fast, so I'll look through all my stuff. All right, I want your attention in 5, 4, 3, 2, 1. Start writing down your notes. All right, so while you get your stuff, transition to notes mode. I'll wait on you. All right, so Kai, Colin, Nick. People take good notes from them, okay? So, Mythbusters, I went through, I'm so sorry, I was doing it really, really late last night, like midnight, making comments. So, if I approved yours, I started really early yesterday and then took a break. But if I approved yours, I said approved, it's a go. If you give me 3 options, I tried to pick one of them. If I felt they were all too low level or I needed more information, I said, please give me more information. If you were still stuck and you're like, I don't know what to do with my life, then go on Chem Matters. Chem Matters is the ACS, American Chemical Society, little magazine article thing, and it will just kind of just give you some ideas to start with, and then you can go on and do something bigger and better, okay? So, if you did not get approved, try to find a new idea today, because Mythbusters Research Brief, sorry, this is a race, Research Brief, which is technically like an introduction to your topic and chemistry behind it and everything, is due Friday. Really short, maybe a page, paragraph, 2 paragraphs, maybe the guts of it though, okay? Because like I said, you're building your paper as you go, so the more you do now, the less you do later. And who wants to do a paper in May? Nobody. Okay? March Madness papers. Okay. So, pre-response is due Friday. Write it down. And write that down. The one you just turned in. I'll scroll up. We have her tutoring today too, and tomorrow. Monday, Wednesday, Thursday. I'm probably going to do like 3 examples of each of these types today, so make sure you're taking down all the examples for yourself for reference. Okay, I'll scroll down for you momentarily. All right, so in a single replacement reaction, we already know about synthesis reactions. We know about decomposition. Pretty much synthesis, you take two things and you make a whole, or you take decomposition, one thing and break it up. Okay, single replacement. Basically, it's a guy. Peter likes this girl. She's already got a boyfriend. Okay, so he's like, hey, I like you, you like me. Let's just go ahead and boot him out. That's basically what's happening. Or it could be the other way. Be girl, girl, guy, guy, girl, guy, whatever. So it's just basically stuff that's replacing other stuff. Now, the other stuff, the free element, these single guys, single girls, they have to be very active. Okay? So if I wanted to boot Logan out of her chair, I'm not going to just look at her and give her the evil eye. She's not going to know to get out of the chair. I have to go physically get up, push her down, and sit in her chair. You have to be active, okay? I can't just sit here and go, okay, it's not going to happen. Unless she's just like, you know, she's just scared, but she's not scared. Okay, so you have to have, you have to have some activity to your free element in order to actually cause that reaction to occur. This is called the activity series, and I'll show you a picture of it in a second. You don't have to memorize it, you just gotta know how to use it, okay? Like the periodic table is a tool, this is gonna be a tool for us, okay? So, the things that replace each other, I know it's the 21st century, okay? We have to be able to replace cations with cations. No cations with anions, just cations and cations replace each other. Boy and boy, switch in the relationship. Boyfriend, girlfriend, boots out the boyfriend, switch with the new guy, okay? So, cations are generally gonna be metals, anions are generally gonna be what? Non-metals. So I say cations and anions, but I mean non-metals and metals. Okay? So in a form like this, A and then B and C. This is the single guy. This is the couple. Okay, so if this is a cation, it's not a cation in this form. It's just a metal that can form a cation. It's a free element. Free elements are not charged. Okay? So if I have this relationship, copper and carbonate. What's that relationship called? Copper 2 carbonate. That's a relationship. Sodium's like, hey carbonate, how you doing? Let me get with that. There we go. Switch. It's a homemaker. It's a Jersey Shore. Really. Yeah. Okay.
There be two sodiums in that relationship?
There would, but I don't have it crisscross. I'm gonna do it right here. Thank you. Okay, so this one, I just had sodium metal, straight sodium, nothing crazy, no charges. B and C were copper 2 carbonate makes what? What did I just make? I switched them back. Sorry. What did I just make?
Copper.
Copper's free, right?
Yeah.
Free agent, looking for a nice friend. And
Carbonate.
also known as Na2CO3. Okay, so sodium is active and it boots copper out of the relationship. So basically what's happening are these two metals, those two things that have the ability to form cations or literally are cations, they've switched places, single replacement. But you have to re-crisscross your charges every single time because they're going to form ionic compounds, okay? So that's why I got this 2 here, because I did a little crisscross action to make sure I got the ionic charges taken care of. So sodium was able to do this. Sodium is more active. The other way around, if I had done copper plus sodium carbonate, yields, what would you expect to form? Copper 2 carbonate, that's what you expect to form, right? This is a big fat lie. Nope, not going to happen. Mainly because copper by itself is going to just glare at Logan. It's just going to glare at sodium. It doesn't have enough energy or activity to boot sodium out of the relationship, out of the bond. So copper is not reactive enough. Sodium is really, really, really active, and it's going to boot copper out so it can take place of it with carbonate. That's called the activity series. Let me show you the metallic activity series, and they'll do the non-metal one. Okay. This is on a reference sheet. I'll always give it to you. Always. What do you notice generally are at the top of the activity series? The alkali metals, right? Why would the alkali metals, why would they be really active?
They can just lose.
Okay, they want to lose electron. They're really high. Kind of high. And they're ionization, so I would say actually kind of low because they're on the left side of the periodic table. So they want to lose one electron. So they're like, yeah, please put me in a bond so I can lose this electron. They want to form an ionic bond. Okay, things at the very bottom of the periodic activity series are things like silver, copper, gold, platinum. Do you ever see those reacting in real life? How does gold react? If it was reacting, my hand would be like falling off, my fingers would be falling off, my ears would be turning green, my neck would be like, scarred. If your metals, like your metallic jewelry, was reactive, you'd be all different kind of colors, falling to pieces. Okay, because it would be reacting with you. So those are generally not reactive. So generally, they'll be the lonely guy in the corner, not with compound. Okay, so those are very special. This is a very special series. We do need to know how to read it based on the arrows. You can see these arrows here, here, and here. They're telling you what they can replace. So, for example, anything from top to here to iron, it looks like. Nope, sorry, to cadmium can replace hydrogen from steam. So it's very special. I'll go through and do a couple of examples with the special arrows that are there as well. Okay, so for the last type of example is non-metal, non-metal. Okay, so anions replace anions. So let's do chlorine gas plus sodium bromide. What would replace what?
Chlorine would replace bromide.
Right, so chlorine is a non-metal. It should be replacing bromine. So what should form?
Sodium chloride and
Bromine diatomic gas, yeah? It's liquid, but whatever, liquid. Okay, so this one should form. And let me tell you that the activity series of this one is really, really easy. Look at the periodic table. You got one out? Who's at the top of the halogen group? Chlorine. Chlorine is the most active of all halogens. Who's right below it? Chlorine. Chlorine is a little bit less active, but still pretty active. And then bromine, and then iodine, yeah? So chlorine, the free one, is more active than bromine, which is why it can boot out bromine from this relationship. If it was the other way around, it wouldn't happen. And I didn't tell you to call this. So this copper plus sodium carbonate one, I told you it didn't happen, right? This is called a no reaction. NR, no reaction. So if I had written this one the opposite way, sodium chloride plus bromine yields something, just put NR, no reaction. Basically, you're telling me like, hey, I'm saying I know how to read the activity series. This is not going to happen. That's what that means. Cool, cool? Okay. So, here's the activity series. This is in order of the PTOE, so that's why I don't go over this one in depth. All right, let's try some of these. Calcium plus water. All right, Lewis, go for it. And I'm going to write it as my funny way of doing it. Do you guys remember that from last week? HOH, okay? I like to write HOH because I want you to see it as a single replacement reaction. It's harder to see it when you write it as H2O. All right, so what do you think is going to happen, Liz? OH. And? Who got booted out? H2, right? Because hydrogen's not a loner. Okay, it's got to have a diatomic as itself. Good job. So we have this thing, metal, that could form a cation, is going to trade places with the actual cation. So don't forget, this is H plus and OH minus that come together to make water. And this cation replaces that cation. They change places. So calcium gets together with hydroxide. Don't forget, calcium has a 2+ charge. That's how that 2 got there. And when H gets booted out, it gets booted out as H2 because it does not do well by itself. Balance it. H2O. That's it, yeah. Because I needed 2 hydroxides and 2 H's. Well, that's 2 waters, so 2 waters. All right, next one. Raise your hand. Who wants to do it? All right, Logan. Zinc plus. Okay. Zinc will replace hydrogen. Okay. almost, because it's got a 2+ charge, right? So zinc is 2+, chlorine is 1-, crisscross, plus what? Beautiful. Okay, so in your head, you were going, oh, this could be a plus. This literally is a plus. This literally is a minus. Replace your cation with cation. Okay, and then re-crisscross. Balance?
2 from HCl.
2 from HCl. Okay, so this is something that you just assumed could happen, but you know what assuming is? Not great. So look at zinc and HCl. Ready? Looking at the activity series and make sure that we're cool to do this. So zinc is here. Can zinc replace H from an acid? Can you see this down here? Yes, it says right here, replace hydrogen from acids, anything from the top of the activity series all the way down there. So zinc's in that spectrum, it's good. But like if you try to do with antimony plus HCl, what would you write? Antimony's right here, by the way. So what?
NR.
Thank you, sorry. Getting old, hard of hearing. Okay, so no reaction. Thumbs up, yeah. This is saying it's something called the She, standard hydrogen electrode. It's just a reference point. It's saying right here, past this point, there's no other thing that can replace that. It's something a little bit bigger than this right here. It's called the She. Okay. Do the first two. Do the first two. With the buddy next to you, take 4 minutes, 3 minutes. Done? No? Okay, so are you excited about reactions? Okay, thank you. All right, thumbs up, you got this. Okay, so for with this one, calcium is the metal. It's going to be able to form a cation. That's the metal. Nitrate, don't be a homewrecker. Leave nitrate alone. Keep it together. It's a happy family. Do not break it up. So nitrate gets just repositioned, and so calcium is then going to position or bond with nitrate, while iron is left all by its lonesome. So we assumed that calcium could replace iron. Can we verify that real fast? I would go back to what? Activity series, right. So calcium is higher than iron. So calcium is higher, calcium is more active. Calcium will boot out iron out of that relationship. Cool, cool? Okay, let's do the next one. If you didn't finish it, we'll do it now. Aluminum. Potassium chloride. Aluminum, potassium chloride. No reaction. Because, what do you notice? This. What do you notice about this? It's an alkali, right? It's an alkali metal. It's very, very, very active. You can probably assume that aluminum is not as active, but then you can verify that. You don't have to memorize this, baby. You just have to know how to use it. Potassium's high, aluminum's low. Potassium will replace aluminum, but not vice versa. Aluminum will not replace potassium. I think I said calcium. Potassium. So aluminum wants to replace it, but no. Potassium is more active, so therefore nothing's going to happen. No reaction. You got that? Thank you. 2, okay. Let's do one more. Yeah, let's do zinc phosphate. Let's do some together quickly, okay? Zinc phosphate, go. Plus magnesium yields. Thoughts? Does it magnesium and zinc? Magnesium, no reaction, right. So you'll notice I'm just kind of putting two together for you here. We have a lot of group 1 and group 2s up top, yeah? Those are really active. They want to lose an electron or lose 2 electrons. Then we start getting to some transition metals. So generally, transition metals are less active, generally, because they're pretty happy where they are. Okay, so zinc phosphate and magnesium would be a no reaction. Yeah? No, I'm totally just lied to you. Thank you. I was thinking the other way around. Magnesium does replace zinc plus magnesium phosphate. My bad. I also have another oops movie I have to tell you guys about. Some people caught last week. Okay, yeah. I'm not perfect, guys. I try my hardest though. Okay, balance. 3 and 3. Yeah, okay. Let's do double replacements. Single replacements, we should be able to look and see cations replace cations, anions replace anions. Let's do double replacements. Okay, double replacements are really, really easy. Everything just switches partners. But there's one little extra thing we have to add to this part of the discussion. Let's see first of all. Let's read it. All right, so double replacement reactions. We have a couple, and they just do-si-do and go find the other partner. That's basically it. Like cations, of course, are always being listed first in an ionic compound. And everything so far, notice most of it's ionic or just straight up metal. So we have a lot of crisscrossing of charges to deal with all the time. So generally we'll have ionic plus an ionic to yield, guess what? Ionic plus an ionic. So we have to do a lot of crisscrossing of charges. I'll have you do an example first, and then I'll tell you about this precipitation deal. All right, so let's do the example I have on the board. Chemical formulas from these two. Go. Cl, that's a 2. I can't. Can you see that? So sorry, here. Copper 2 chloride, yeah? And? Sodium carbonate. Okay. It's in your best interest to put parentheses around your polyatomics, okay? Because you won't be a home wrecker and break them up. So chlorine, that's fine. Carbonate, put a parentheses around it so you do not break it up. So we have plus minus cation anion plus minus cation anion. So who is this cation going to repair with? Oops. Carbonate. Stop too short. Carbonate. So copper carbonate? Is that how you say that? Copper 2 carbonate. Right. Copper 2 carbonate. Where are the 2's? Yeah, reduced down to 1. Okay, so there's copper 2 carbonate. And then what is this cation going to pair with? Chlorine. So plus NaCl. 1 plus 1 minus, that's why I have no charges indicated there. If you write ClNa, look how ugly that is. Doesn't it look ugly? Okay, it looks ugly. If it looks ugly, it's probably wrong. That's how I look at y'all's work and figure out if it's right or wrong. If it's ugly, it's wrong. You just start to see things as like, oh no, that doesn't look like anything I've ever written before. It's probably not right. Okay, so it's just cations and cations switch places. So in this case, one of these is going to be aqueous, and one of these is going to be precipitate. So how would you figure out if one was a precipitate or not? You need to know these solubility rules. Basically, if something is soluble in water, how do you denote that as a subscript? Which of these? AQ, right. You write AQ to tell me it's soluble, it will ionize in water. If it's insoluble, that means it's going to form a solid in water, which you denote as PPT, precipitate. So let's look at the solubility rules, and you guys tell me which of these is the precipitate. Solubility rules. Notice lots of polyatomics. So basically what you'll do is you'll say, okay, I have a carbonate and I have a chloride, yeah? I have a carbonate and a chloride that I'm dealing with. Chlorides, what's the rule for chlorides? They're always soluble except for lead, mercury, and silver. Yeah, lead, mercury, and silver. Okay, basically if you have a heavy metal, lead, mercury, or silver, be very suspicious of it. It's probably going to be a precipitate. Those just commonly are going to drop to the bottom of a test tube. They don't dissolve well. But that kind of makes sense. Heavy metals just don't dissolve well. That's why they're like in your well water and they're used for jewelry. That's just how they are. But carbonates. Carbonate was another one. Carbonates are generally insoluble. So most of your carbonates are going to be precipitates, except for ammonium carbonate or anything that's an alkali metal carbonate. So if I say sodium carbonate, soluble or insoluble? Sodium carbonate. It's actually soluble, right? Because all carbonates are insoluble except for, all carbonates are insoluble except for ammonium carbonate and any alkali metal carbonate. Okay, so sodium carbonate's good. It's going to be soluble. But like copper 2 carbonate, it's not on the exception list, right? So it's going to be a precipitate. Does that make sense? Yeah.
Do we have to know these?
I'm still working on figuring out if I'm going to give you the list. I'll probably give you the list. Because it's one of those things that you only have so much storage space. Okay. As long as you know how to use them. If you don't know how to use this, that's on you. Yeah.
So do you remember all these sections?
Mm-hmm.
All of them?
I have an AP, you have to memorize them. At least you used to. So this little Cashingia thing down here. Chlorates, acetates, sulfates, halides, nitrates, group 1 in ammonia, those are all soluble with some exceptions. Carbonates, hydroxides, oxides, phosphates, sulfides. All insoluble with exceptions. So I made it up for them. I'm not going to teach you guys that. Okay, so from these, look at the nitrates. So let's look at nitrates. Tell me if it's soluble or insoluble. Ready? Calcium nitrate. All nitrates are soluble, okay? All of them. Always soluble. Okay. So this one's soluble. Iron 2 chloride. Ready? Insoluble?
Soluble.
Actually, yeah, you're only your heavy metals, silver, lead, and mercury are going to be the ones that are not soluble. So chlorides, generally, halides are halogens, like chlorides, bromides, iodides, and fluorides are generally soluble. Magnesium phosphate. Ready? Magnesium phosphate. Oops, wrong way. Magnesium phosphate's insoluble, except for the GIA, which is group 1 in ammonia. So no, magnesium's not in group 1. It's in group 2. So that one's going to be insoluble. Insoluble. So as long as you can use a list, you're in a good place. All right, let's do some double replacements. Silver nitrate, go. Tell me the formula.
AG 2.
NO3, 1 and 1, right? If you have to guess a charge, guess a 1. Most of them have most of your products all in 1. 50% of your products have a 1 minus charge. Okay, silver nitrate. Silver number 1, remember that? I don't have to tell you silver's number 1. 50-50, yes, yeah. Go with 1. Okay, sodium chloride. Right. How do you know this is not ClO3? Ide, right. Ide means look at the PTOE and get that symbol with its charge. Okay, forms. So if you've got to do this for yourself to make yourself successful, I was in your place once. I literally did this every single time I did a double replacement. I was like, okay, this is the cation. It's going to pair with another anion. Boom. Silver, 1 plus, chlorine, 1 minus, silver chloride. And what? Na? NO3. Right. Don't be a homewrecker. Leave nitrate alone. Okay, balanced? Yes. Okay, so step 1, Friedel reaction. BCE. Is it balanced? Yes. Step 2, check solubility rules. Is it not balanced? Yes, balanced.
Yes, no.
Okay.
AgCl is not balanced.
Oh, good job. Yes, so this one's going to be our precipitate because our lead, silver, and mercury are generally going to be suspicious, and you want to go ahead and make them insoluble. All nitrates are what? Soluble. Let's go back and verify that. So we're looking at nitrates and chlorides. Nitrates, soluble. Chlorides, soluble, except for those couple of things. Oh. So that's how you say precipitate, because it's an exception to the rules. Thumbs up, you got this. All right, I need more thumbs. Let's do another. Lead 2 nitrate plus magnesium chloride. I'm going through nomenclature very quickly. Go. PB. Okay. F2. That fluorvium. What's that called? Fluorvium? Fluorvium. Fluorvium?
What charge is
Fluorvium. Fluorvium. F2. Okay. So, double replace that baby. PbF2, and remind yourself, Pb was a 2 plus because I told it to you. Chlorine was a 1 minus because it says on the periodic table, crisscross, and what? MgNO3 2. Okay, if you had to pick one, hold on, MgNO3 2. If you had to pick one to be an absolute aqueous one, which one would it be? Nitrates are always soluble. Good. Lead, usually suspicious. Let's go with precipitate, okay? So there are some general rules, and fluorides are not on the other rule set, so that's why I'm not going back. Okay. So notice over here, this lead, it's with a nitrate. Nitrate rules. Nitrates are soluble, so that's why that one's aqueous. And this one's aqueous because it's aqueous. Because it's hard to react two solids. They don't get together well. 2 aqueous solutions do blend well. All right, so you guys do this one, and then take a break, and we'll do combustion. We already combusted the bottle like a million times last week, so we did. We combusted the alcohol. Do that one for me. If you finish this, stand up, take a break. Keith's going to write this on the board for us, and we'll check it. And then we'll do combustion. some junk jacks, get some water. I know it's Monday. We're supposed to stay up too late last night. Horrible idea. Hindsight's 2020. Talk to your Mythbusters partner about life. Alright, take a break for 1 more minute. Thank you.
It says that I didn't turn in my Mythbusters thingy, but I did.
Did it have your name on it? Was it on the document? Was it a separate document?
Oh,
Did
it
you
didn't have
submit
the
it?
name on my document.
Okay. Did it say, what were the ideas? 'Cause I remember one had their name, I had no idea who it was from.
Oh,
Because if you download it from the Google Classroom, it's automatically put your name on it. That's why I had you go to Google Classroom. You made your own document, share with me, their name on it, I have no idea who's it is.
let me check. The lemonade with the
Okie dokie artichokes. Okay. I don't want to like snap at you or clap at you, okay? That's like elementary school. All right, so we got balanced all the way. Acetates are usually always soluble, so I'm going to put aqueous here. And then chlorates are also always soluble, so I'm going to put aqueous here. You're going to assume that your reactants start off as aqueous, 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 because it's hard to react to solid things. So what happens is, here's what you're looking at, okay? Visualize this. You take a little liquid, you pour it in something. You take another little liquid, you pour it in something. And guess what it looks like? 2 liquids. Did a reaction actually happen? What are the evidences of chemical reactions? Bubbling, precipitate, heat, fire, flame, smell. Did anything happen? So what would you classify this as? A reaction. If you end with 2 aqueous products, you go ahead and assume nothing happened. They're just all floating in there together. Nobody's reacting with anybody. They're just floating. And I'm going to talk about NIEs or net ionic equations tomorrow, and this will make a lot more sense. But if you make 2 aqueous things, nothing actually happened. It was all just built up all this anxiety over nothing. Yeah. No, 2 precipitates is like, hey, I've got 2 things that are insoluble. Precipitate, precipitate. That's assuming you make two new compounds. Okay, we're going to practice that some more later. Combustion, last time. Combustion. And I'll let you guys practice. All right, so combustion means reacts with oxygen. What in your body do you think of? It has to do with air. What kind? Cellular aerobic respiration, right? Aerobic respiration, biology. I know you remember it. What does the oxygen react with in the cell, in the mitochondria? Glucose, which is kind of like a hydrocarbon. It's just that's an oxyhydrocarbon. Oh, can you have that? I was looking at this whole thing. This is mine. Okay. No, I bet you. My dog was probably distracting me, and I blame him. Okay. Oh God. Great day. This is fun. Think about tower over there. Did I check all this stuff on passing by? What is the question? I don't believe I did. Pretty sure this has no grades on it. Nope. Okay. Ready? Thank you. Okay, so combustion reacts with oxygen. Anytime you see oxygen, or if I say combust, you read between the lines, oh, she means reacts with oxygen. Because I'm not going to say, hey, Sam, that butane, it's gonna combust. I'm going to say, no, I'm sorry. I'm not going to say butane reacts with oxygen. I'm going to say butane combust. All right, so this one right here, what does this remind you of? What other type of chemical reaction? Synthesis. This one, the combustion of metals is simply a synthesis reaction. It's just two things come into one. So this one, let's do barium plus oxygen yields what? Barium oxide. Formula? BaO. Okay, so there are 2 and 2 cancel each other out. 2 here, 2 there. All right, so solid barium reacts with gaseous oxygen to make solid barium oxide. All right, so the true combustion ones is when you react with hydrocarbons, because that's when you get the fire and flame and all that jazz, right? So you got to make sure you have a lot of energy to make that fire and flame. Where's the energy coming from in these reactants? Not oxygen. This is a fuel source, okay? Like glucose. Glucose is a fuel source. Gasoline is just a bunch of hydrocarbons lined up together. It's a fuel source. This fuel source has tons of energy stored within it. The potential energy is in between the bonds. So carbon to carbon infinity, okay, that can happen a million times. That's where the energy is formed and stored in those bonds. It's called chemical energy or potential energy. Okay, so I know this is kind of like the whole hydroxide debate where you're like, oh, hydroxide, HO. No, OH, right? This one says hydrocarbon, so you think HC, but no, we write CH. Okay, so let's do ethane. Ethane. C2, ane. What was the rule for anes? Okay, it is H6, but what's the rule? They're all single bonds, so anes are all single bonds, and the rule for that to get to hydrogens are 2N plus 2. Okay, enes, 2N, and then ines, Y-N-E, minus 2, 2 and minus 2. So that's how you get your nomenclature back into practice here. Okay, so ethane plus oxygen yields carbon dioxide plus water. This is a memorization, but I mean, it's not really memorization. You know most of this from biology. It's just biology made 36 ATP while we make a bunch of fire. Okay, so first thing you want to do, this is how I would do the balanced chemical equation. C, H's, and then O's. The reason I say save O's for last are because O's are in 2 places over here. So if you balance it first and you put a subscript and then you get another coefficient, you tend to mess up your options really fast. So balance your carbons first. What do you want to do? 2. Balance your H's. 3. How many oxygens over here? 7. 3 times 1 is 3. 2 times 2 is 4. So 3 plus 4 is 7. Okay, how are you going to get 7 out of 2 over here? What times 2 is 7?
Well, you do the boost time on multiple, right?
Okay, hold on. Wait for that. So normally 2 times something is 7. That's a 3.5, right? But you shall not put decimals or fractions as coefficients, okay? So 3.5 needs to be brought up to the least common multiple. I feel like that's what it's supposed to be called. Okay, so basically if you ever get something that's a 0.5, you got to multiply it by 2 to get it to a whole integer, yes? If you multiply that one by 2, you multiply the whole shebang by 2. So this one is a 7. This one was a 1, now is a 2. This one was a 2, and now is a 4. And this one was a 3, but now is a 6. Okay, so the ratio is 2 to 7 to 4 to 6. So anytime you want to put a decimal, just do it, and then multiply everything by 2. So that's why combustions are a little bit more tricky. I always save the oxygens for last. All right, let's practice. Yeah.
About the first one, how did you know that because like barium is a solid and oxygen is a gas, how did you know that reacts to bases?
Because ionic things are generally solid unless mixed in liquid. So those that they're solid and gas, I see no liquid, right? No water, no aqueous, no nothing. So I'm assuming it's just in its ionic room temperature form, which are solids. All ionic forms are solid. Good question, because we're going to have some with aqueous. All right, oh, we just did that. All right, let's do aluminum combust. Go, ready.
AL2.
Al2,
Wait, no. Yeah.
O3, good. You're crisscrossing in your head. Aluminum's a 3 plus, oxygen's a 2 minus. Crisscross. Balance. Wait. Balance.
2 on the outside. 3 on the 3.
2 on the side, I like. Okay. And a,
And 4 on the
right. I knew it was a 4, so I didn't want to write 2 yet. All right, so there's a 4-3-2 ratio. All right, octane is a liquid. Yes, octane. Oct means 8. How many hydrogens? All right, so you're doing 2n plus 2 to get the ane H's, so that's 18. Combust. 2. Always makes what? Always. CO2 and water. This one will be easy to get because it's always going to yield the same thing. Okay, but not all combustions always yield carbon dioxide and water. Only combustions of hydrocarbons does that occur. Okay, carbons first. Go. Balance. 8. And then hydrogens. 9. You're a struggle bus there. Okay, 9. All right. How many oxygens total here?
25.
25. 8 times 2. Don't forget the subscript. Don't be neglecting. So that's 16 plus 9 times 1. 25. All right. So how am I going to get 25 out of 2 here?
Multiply by 12.5.
Multiply by 12.5 or 25 over 2, yeah? 25 over 2 is 12.5. I'm just trying some new stuff, just to keep it interesting. So I can't have a fraction, nor can I have a decimal. What do? All right, multiply everything by 2. So multiply 25 and a half, or 25 halves by 2 is 25. This one's a 2. This one's a 16, and this one's a 18. Big numbers, 2 to 25 to 16 to 18 ratio. All right. Are we at 20 minutes? You guys will get the practice ones that I didn't put on homework because I was hoping we could get them done in class. Done right now. Oh no, just tell me the formula for pentene real fast. Just kind of want to make sure you know it.
C5.
H10. Because ene is a 2n. Yne would be at 2n minus 2. All right, so you guys have, I'll show you the video at the end. You guys have this printed, and if you don't, I'm leaving it right here for you. I would start with single, and then do double, and then do combustion. If you want to write out the chemical equations for all of them, and then do the activity series and the W, that's fine. But you have your book that you want to do it later. Yeah. an organic type of carbon. But yeah, you want to take phosphate, sulfate, generally. How many? That's why I tell my biology students never understand they don't know what phosphate is. I'm like, it's carbohydrate. It's got 8 in it. It's got oxygen.
Did you like see in the polyatomic how many oxygens there are looking by looking at the cation?
I don't think so. You could get the tar really in the most likely. I don't know. Who cares? If you know the balance formula. I'm crisscrossing. You know, that's the, you know how to do that. Hey.
Do you want me to tell you, the three,
I want you to resubmit on Google.
like with the name?
Yeah, and if you want to get on my Google Classroom, go to the computer right now, so you're going to do it.
Like right now?
Yeah, you and Jeremiah have to go to the back. If that's what you're doing, you're doing as a partnership. Literally, go on Pin Matters. Go on Google Pin Matters at Carnegie. Like Chemistry Magazine, and I'm looking, that's one of my first suggestions, and I don't want to give ideas, because I want something very exciting that you're excited, not that I'm excited about, I mean, I just have to grade it. I know, however, find something else to do. It's food, attentiveness to light, do something else with it, but don't go and toss it.
That's more like
You can relate to psychology. This is chemistry of the mind. Yeah.
Isn't zinc the only thing that's in metals that has a 2 plus?
And cadmium.
Oh,
Jeremiah, you guys, is it turned on? I did update all the grades this weekend. If there's something amiss, please let me know. 500 grades in. There's bound to be a slip up. Please make sure. Oops. Oh my God, what have I done? No! Okay, let me stop videoing. Hold on.